We've learned about object detection, which draws bounding boxes around objects. But what if we need an even more precise understanding of an image? That's where semantic segmentation comes in. Semantic segmentation goes beyond bounding boxes. It's a pixel-level classification task, meaning every single pixel in an image is assigned a class label. Instead of just knowing there's a car in the image and its general location, semantic segmentation identifies which exact pixels belong to the car category, distinct from the road, sky, or other objects. Think of it as creating a mask for each object category in an image. If you have an image of a street, semantic segmentation might output masks for road, sidewalk, building, car, and person, with each pixel colored according to its category. This provides a very granular and detailed understanding of the scene. Common architectures for semantic segmentation include fully convolutional networks, FCNs, and UNIT. These networks typically use an encoder-decoder structure. The encoder part acts like a standard CNN, extracting features and downsampling the image. The decoder then upsamples these features, reconstructing the image while performing pixel-wise classification. A popular technique within these architectures is skip connections, where information from the encoder is directly passed to corresponding layers in the decoder. This helps the network retain fine-grained spatial information that might be lost during downsampling, leading to more precise segmentation masks. Semantic segmentation has critical applications. In autonomous driving, it helps cars understand every part of their environment: road, lane markings, obstacles, pedestrians. In medical imaging, it precisely delineates tumors or organs. In satellite imagery, it maps land use. It's a powerful tool for detailed scene understanding. Next, we'll summarize broader applications of computer vision.